So from what you have read and understood from physics learned so far, I'm assuming that you have just, you know, completed your class 10 and you're in your class 11th. So what do you think is coefficient of restitution? And how would we apply this in the given problem here? Let me also give you a little bit of clarification from my end while we prepare for this question, this problem here. We are not exclusively using coefficient of restitution to solve this question. No, this is actually this is just a minor tweak to to just to make your thoughts more vibrant, just to make sure that you are able to connect many topics, as many topics as possible in one problem. Unlike the previous three methods, where using loss of using equations of motion, using conservation of mechanical energy, and using work energy power, we did solve the questions exclusively using those concepts. Unlike here, where we are just trying to bring in something which actually is not needed at all. So by the end of the solution, you might be like, what, this is not required. You could just do it the other way around as well. Yes, of course. So just a minor tweak. So I'm forcing coefficient of restitution to be pulled into this question here. The purpose is not to make you spend some time on things that are not exclusive on a concept, but rather is to make sure that you understand the implication of collision and coefficient of restitution whenever you see a problem that is based on an object being dropped, hitting a floor, or a bullet hitting a block, or maybe a car hitting a wall, things like that. Okay? So apologies in advance. Having said that, let's try to understand what coefficient of restitution is first. So coefficient of restitution is a number that tells us how bouncy a collision is. It compares how fast objects separate after hitting compared to how fast they were approaching before hitting. In other words, relative speed after collision by relative speed before collision. So if one object hits a wall or ground, if that object speed is zero, then E is equal to speed after rebound by speed before rebound. This is where it gets related to our problem here. Now the question, what does bouncy means? It actually means the amount of speed the object is keeping after getting hit to a surface. For instance, think of a rubber ball which is dropped from a height of 1 meter. It's dropped down, it reaches the floor, it hits the ground. If this ball comes back to 1 meter, the same height from which it is dropped, this collision is perfectly bouncy. Instead, if it comes back only to 0.5 meter, so it is dropped, it comes back only up to zero point 0.5 meter, not up to 1 meter, come back only to 0.5 meter, it is half as bouncy as in the first case. Now, third case, if it doesn't bounce at all, it's not bouncy, which means you drop it from 1 meter and it just gets embedded in the wall or in the floor. It doesn't bounce at all. And this bounciness can actually be measured by a number, which is what we call as coefficient of restitution. Now it has a range. E, if equal to 1, means this perfect bounce, there is no energy lost. If it is equal to 0.8, it is mostly bouncy. If it is 0.5 instead, it is half bouncy. And if E is 0, which is the lowest in the range here, it is not bouncy at all. Okay? Now you'll be able to connect what you have read to what actually the concept is, right? Which is this bounciness can be considered to be, can be explained with the type of collision where E is equal to 1 means it is perfectly elastic. Okay. E is equal to 0 means the collision is perfectly inelastic. And the real time collisions, the one we see in the real life, being E between the range of 0 to 1, making it partially elastic. Now, don't worry, more on this when we discuss work, energy, and power. Just go through this solution one more time. Try to understand what is the range of E, what is the physical implication of having the value E is equal to 0 to E is equal to 1, and what do we call them specifically as perfectly inelastic, perfectly elastic, and elastic collisions. Okay, try to visualize the examples given, try to connect that to the given question. And when we discuss collisions in detail, we go through a new, I think I have around 15 to 20 questions, which would give you a very deep insight about coefficient of restitution. We will explore each and every word there. Why is it coefficient? Why is it restitution? Why is it elastic? Why is it inelastic? Why is it perfectly elastic? We'll go through each and every word there and try to emphasize the significance of it. Okay. Now, here what we'll do is we'll find V1 and V2 in terms of H1 and H2. When an object falls freely from rest, its speeds just before hitting the ground is V1 is equal to root 2 GH, and V2 for a different body will be root of 2GH2. How? Come on, we just discussed this so far using lots of equations of motion, or can also be by conservation of mechanical energy, or for that matter, using work energy theorem. Now, if we put this into the formula, which is V2 and V1, we know that V2 is root of 2GH2 and V1 is root of 2GH1. If you plug these two values into V2 and V1, what we get is E is equal to root of 2GH2 by root of 2GH1. And if we cancel root 2G, what we get is E is equal to root of H2 by H1. Now, how is this relevant in the context of the given problem? What does the problem says here? A spherical body is dropped from a height of 10 meter. H1 is 10 meter. It rebounds to a height of 5 meter. H2 here is 5 meter. Impulse, which is actually change in velocity, is can be expressed as change in height. Why? H2 is 10 meter and H1 is 5 meter. So E can be used to find out H2 and H1 can be used to find out E instead of velocities, 10 meter and 5 meter instead. Okay. Now, exactly this is what I was trying to tell you. This is not an exclusive way of solving the question. It is instead just forcefully bringing in coefficient of restitution for no specific intent. But as I said, it's another way of looking at things, which is what primarily GE Advanced is about. Okay. Now, when the ball hits the ground and rebounds, H1 is 10 meter and the rebound height H2 is 5 meter, right? Now we'll apply the shortcut. H2 by H1 is now 5 by 10, which is root of 1 by 2, root of 0.5, which is approximately 0.707. What is the meaning of E is equal to 0.707? It means that the ball keeps 70.7% of its initial velocity after bouncing. So the ball is dropped from a height with it hits the floor with some velocity, let's say x. 70% of that x is retained after the ball leaves the surface. I hope that makes sense. Think of this. Go back to the explanation one more time. Go back to the table that you have written down. If you haven't, Please do make a note of this. And then try to say, oh, E is equal to 0.7. What would that mean? E is equal to 1. What would that mean? Right? E is equal to 1 means the ball has retained the complete velocity after the collision. Right? Things like that. Okay. Now, from definition, we have V2 is equal to E times V1, which is V2 is equal to V1 is 0. E is 0.707 times V1. So V2 is 9.9. So 9.9 is 0.707 times V1, and therefore V1 is 9.9 by 0.707. It's approximately 41. Okay. Now, this is where we find out V2 using equations of motion or using work energy theorem. Okay. So now, once we have V1, we can link V2 and V1 to find out the impulse in the equation. Why? Because impulse J is mass into velocity final minus velocity initial, which is V2 minus V1 minus times minus is plus. So this is V1 plus V2. Now, what is V2? V2 is, wait, give me a second here. Yeah, V2 is E times V1, right? So I need some clarification here. Yeah, impulses mass times V1 plus V2 here can be written as V1 plus V2. Okay. Oh, is there a mistake here that I've done? Yeah. So instead of this V2, we can plug in E times V1. So this V2 is E times V1. And then what we what we get is, okay, that makes sense. So V1 and V1 is common here. So I can pull out V1 from the bracket here. So that becomes M times V1 into 1 plus E, which gives us V1 M times V1 1 plus E. E is 0.707. So that becomes 1.707. 0.1 into V1. V1 we already know is 14. So it is 0.1 into 14 into 1.707, which gives us 2.39. Okay. So yes, so actually, what was when I was telling you that this is not a direct way of doing the question using coefficient of restitution alone, I mean, you can convert this complete equation in terms of E and V1 alone. We don't need the second velocity V2. V2 has been expressed in terms of V1 and E. But to find V1, you will definitely have to use equations of motion or work energy theorem or conservation of mechanical energy. Okay. But yes, to link this concept. So the next time, whenever you see the equation of impulse, if there is an object colliding another object, what should come into your mind? Another way of looking at things, which is coefficient of restitution based on collision. What we learn in work energy part, which is applied in questions that is based on loss of motion or maybe motion in a straight line. Okay. Apologies for a bit of uh, lack of clarity here. This is what happens primarily when discuss things based out of presentations. While we do the written calculations, I think if you have any confusion here that I've made from my end, apologies. I'll make sure that that doesn't appear for or address that while we discuss the written part of the solution. All right. So now let's go into the numerical part.